In this video, we are going to discuss scatterplots and measure of correlations. These are tools that we can use to visualize or have an overview on the relationship between two variables. To learn about these, we are going to use some data from Yelp.com, and we're going to ask a very straightforward question. Do users put more effort into writing reviews for good bars or for bad ones? Here, we are going to measure the effort that a user puts in as the average number of words per review for that bar. So if a review has a lot of words, we consider that the user put a lot of efforts in writing the review. We're going to measure whether it's a good bar or a bad bar based on the average rating on Yelp. The bars that we're going to look at today, they are all in Madison, generally in the capital area, and specifically more of them are on State Street, right between the campus and the Capitol. We're going to have 2,900 reviews. They were written by 1,600 users, and we have 64 bars in the dataset. If we want to begin to understand this relationship, one thing that we could do is simply put all of our data into a PowerPoint slide, like here, and we could look at it. Admittedly, this isn't a great way to understand the relationship between two variables. Even though I've sorted the data here in descending order by average number of stars, it's still not clear that there is a relationship between the ratings and the words per review. We can see that the Up North bar and the Comedy Club are the two highest rated bars in the State Street corridor. Meanwhile, the Kimia Lounge, which has closed down, the pub and the KK were the lowest rated bars in the dataset. That is some information, but that doesn't help us generally understand the relationship of interest, which is the relationship between average ratings and the average number of words per review. So what can we do instead? Well, we can create a scatterplot. A scatterplot is a graphical representation of the relationship between two variables. It's useful for understanding four things. First, it's useful for understanding the magnitude and the direction of the relationship. On average, does X increase a lot as Y increases? Does it increase a little bit? Or does it decrease as Y increases? It's useful for understanding the strength of the correlation between those two variables. That is, among other things, how tightly packed are the points around the line. It's useful for visualizing the linearity or the nonlinearity or even curvilinear relationship between the points. So do the points follow a straight line or a nonlinear line or a curvilinear line? Then finally, it's useful for visualizing the outliers. Outliers are points that deviate from the overall pattern in the data. As we go deeper through this video, we are going to spend more time discussing each of those points and hopefully you will get an intuitive sense of what they mean. Let's take a second to actually look at a scatterplot. Without any data on it, this is what the scatterplot looks like. We have the title up at the top telling us that we're going to look at the average rating for bars in the capital area versus the average number of words per review. On the y-axis, on the left-hand side, we have the y-axis label. That is the average words per review. On the bottom, we have our x-axis label, which is the average rating, and it goes from 0 to 5. And now that we have this, we can start adding points. Up North bar was the bar that had the highest average rating. It had 4.44 stars and it had 80 words per review. So if we simply line up 4.44 on the x-axis and 80 on the y-axis, that's where the point goes. Then, as we add more points to this plot, we can start to understand the relationship between X and Y, the relationship between average words per review and average rating. How to interpret the scatterplot? Before I just give you the answer, now will be a good time to pause this video and to think about what you can safely infer based on what you know right now. if you are watching this video with someone else, you can exchange your thoughts. Think about the magnitude and the direction of the slope. Think about the strength of the correlation, the linearity, and the outliers. Pause the video, spend a few minutes, write down what you think and different aspects of the relationship. Then write down something that you can't infer based on the information that's on the right-hand side of the screen right now. Once you're done, you can continue watching the video and we'll discuss each of these points. First, let's talk a bit about the slope, specifically about the magnitude and the direction of a slope. While the vocabulary varies across disciplines, magnitude generally means how big is a number. For instance, when we talk about the magnitude of a correlation, it is the correlation number, how strong it is. In our case, we are focusing on the slope, so the magnitude of the slope means how steep it is. On the plots on the right and on the left side, the slope is moderately steep, so the magnitude of the slope is not too strong. In the middle plot, however, we have a stronger magnitude because the slope is quite steep. Concerning the direction, it just means that we want to know if the slope goes up or down. If it goes up, we have a positive slope, or we can say we have a positive correlation. This is the case in the first two plots. If it goes down, like in the last plot, we have a negative slope, and we can say we have a negative correlation. If it is flat, we have a horizontal line. This is one of the cases where we have no correlation. All of these cases can be visualized easily by adding a trend line to the plot, and we are commenting on the slope of this line. Let's go ahead and look at the variables of interest, the average ratings and the average number of words per review. First, let's find the line that best summarizes this relationship. For now, I'll just tell you that this is known as the line of best fit or the trend line. Next week, we are going to spend some time quantifying that and discussing exactly how it's defined. But in general, just know that this is a straight line that best defines the point on this plot. And what I mean by that is that if we change this trend line, we may be able to fit some of the points better at certain angles. They will be closer to the line, but overall it offers a worse reflection of the data. So in our case, it seems that the slope has a moderate magnitude and that the correlation is positive. The slope is going upward to the right. That means that, on average, when there are more words per review, we expect to see a slightly higher average rating. I say on average here, and this is important because this is not always true. There are several examples with high ratings and shorter reviews. Now I want to talk about correlation. A correlation is the strength of a linear relationship. The correlation is how closely related the values of x and y are in the case of a linear relationship. Closely related values will produce points that are much closer to a line. We say in that case that they have a strong correlation. On the other hand, less closely related values, less strongly correlated values, will produce a more dispersed cloud of points, or they will not follow a line. We say that the variables are weakly correlated in that case. Now, correlation is measured by a correlation coefficient, and the equation is right here on the slide for you. I want to take this moment to make a few points. First, in this class, I will generally not ask you to memorize a lot of equations, and this is one example of this. I will not ask you to memorize and regurgitate the mathematics behind the correlation coefficient. However, what I will ask you to do is to understand some of the properties of this equation. Here, the correlation coefficient has some very nice properties. First, it's always a number between -1 and 1. A correlation of exactly 1 or of exactly -1 indicates that the points are exactly on a line and that this line is not flat. If it's 1, it means the line goes up. If it's -1, the line goes down. So the sign indicates the direction of that relationship. In the case of a positive correlation, so a number between 0 and 1, when x grows larger, on average, y tends to be larger as well. On the other hand, if the value is between 0 and -1, so it's negative, it means that when x grows larger, y tends to be smaller on average. Here are a few examples to help you distinguish between the correlation and the magnitude of the slope. Remember, correlation is about how tightly packed the points are around a line. In the first two graphs, the points are on average at the same distance to the line on the graph on the left and on the right. So it means that these graphs show similar correlations. However, the second slope is steeper, so this slope has a stronger magnitude, but the correlation is the same. On the bottom graphs, the slopes are identical, so we have the same slope magnitudes. However, the points are less tightly packed around the line in the second graph, so they represent a weaker correlation. So in the bottom graphs, we have the same slope magnitudes, but a weaker correlation in the second graph. Here are two special cases that often create confusion, but they are actually pretty simple, so they shouldn't. What do you think are the correlations in these two graphs? In the first graph, on the left, there is definitely a strong relationship between the two variables. If you give me the value for x, I should be able to guess what the value for y is a lot better than if I didn't know x. So there is a relationship. However, if I have to look at the line of best fit, would it be going upward or downward or be flat? It's not clear. How close would the point in the scatter plot be to the line for each of these cases? Well, here is a line of best fit, and as you see, the best we can do is to draw a flat line. So there is no correlation between these variables. That's why it's important to remember that the correlation is the measure of the strength of a linear relationship. If you see a correlation of 0, it does not mean that there is no statistical relationship. It just means that there is no linear relationship. Now, look at the second graph. It seems that the points are tightly packed around a vertical line, so you might think there is a strong correlation, right? Tightly packed means strong correlation. But I want you to ask yourself, if I give you x, does it help you guessing what y is? If I tell you that x is 0.1, are you any better to guess what y could be than if I didn't tell you anything about x? It seems in that case that knowing x doesn't help, so there is no relationship between the variables and the line of best fit is actually flat. So there is no correlation in this case either. So remember two things. The correlation is a measure of the strength of a linear relationship. So it's good at capturing only relationships where the points fit around a line. And the line should not be horizontal or vertical, but it should be either going upward or downward. Let's take a look at the correlation between the variables we are interested in. This is the data we have about average ratings and the number of words per review. It does look correlated. It's not that strongly correlated, but it's not that weakly correlated either. We can see a trend here. Let's fade that into the background and look at the different levels of correlation that we might have found. First, we can have perfect correlation. Perfect correlation has a value of either exactly -1 or exactly 1. It means that all of the points fall exactly on a straight line. Now, to be honest, this is something that you are unlikely to ever see as an analyst. If you do see it, it's actually likely that you've made some error in the coding or in the plot, because in most things that are of interest to an analyst, there are some variations or noise in the data. Even in manufacturing, where we shoot for things like Six Sigma accuracy and very, very low error rates, there are still some acceptable levels of tolerance in the manufacturing precision, which would mean that we don't have perfect correlation. So remember, perfect correlation means that it falls on a straight line, but it's something that you're rather unlikely to see. The next thing that we can talk about in terms of correlation is that there is no linear relationship between X and Y. It could be completely random, or it could be one of the nonlinear cases with a correlation of 0. This would be, for instance, a cloud with no discernible direction, and that changing the value of X has no predictable effect on what you would predict for the value of Y. This is another thing that you're very unlikely to see in practice. In practice, there tends to be some relationship between two variables, even if it's just by chance. And in the case where it's due by chance, we call it a spurious correlation. But anyway, there is always, almost always, some level of correlation between two variables. Now we can talk a bit more about linearity and nonlinearity. Linear relationships produce points clustered around a straight line. Nonlinear relationships produce points that follow either a curved line or other patterns. This is really important for when we get to regression in the coming weeks, and that's because we can't use linear methods to quantify nonlinear relationships. This is why it's so important to plot your data with a scatter plot and see what it looks like. Much of the regression techniques that we'll learn initially are only valid for linear relationship. I'll show you later in the semester how to augment them in a few ways to work with specific types of nonlinear relationships. If we try to apply linear models to nonlinear relationships, we end up with incorrect conclusions, invalid predictions, and from a business standpoint, decisions and actions that can end up costing us a lot of money. Indeed, if we're doing analytics to help businesses make better fact-based decisions, if we come to incorrect conclusions and invalid predictions, that means we are going to make potentially errors that are very expensive. Let's take a look at this in the context of the Yelp data. Well, some students, when they look at this, they see a straight line that could go from the bottom left to somewhere up near the top right. But other students might say it could also be a nonlinear relationship where it goes from the bottom left and then up and then down again. This is one of the things that we're going to do a lot throughout the semester. We're going to look at real-world data, and so we'll see that in many cases things are a bit ambiguous. For the sake of just understanding what linear and nonlinear relationships actually look like, we are going to create some simulated data that have a more obvious relationship to it. These blue points, for instance, follow a very obviously linear relationship. You can put a straight line right through them, and the pattern generally tends to fall around that straight line. We can say in that case that we have a linear relationship. Alternatively, we can have some other points, like the black points here, that follow very obviously a nonlinear relationship, a nonlinear pattern. That is, when the average ratings are low and increase here, average words per review tend to increase at first until we get at about 3 stars, and past 3 stars, they begin to decrease again. Now, here is a challenge. If we put that same straight line on these black points, which is what linear regression does, you can see that it does a very bad job at predicting where those points are going to fall on the plot. It's actually missing the vast majority of those points, despite being the best linear representation of that data. Instead, what we could do is put a nonlinear relationship on the points. In that case, the points don't form a roughly straight line, they form a curvilinear line. I will show you later in the semester how to do that with regression, and it turns out that it's actually quite simple. Finally, we are going to talk about outliers. An outlier is a point that falls outside the general pattern that you can see in the data. How we are going to handle them depends on what our goal is and what the underlying cause of that outlier is. Sometimes we're just going to delete them. We might delete outliers if the data point is not relevant to the topic of study. The example that I like to give for this one is, imagine that your younger sibling comes to you and says, "Hey, I've decided I know what I want to do when I go to college. I want to study geography, but I'm concerned about my career prospects." You say, well, we could collect some data and we could look at what different geography majors at various universities make. That might help pick the university that you want to go to. So you go out and you get a random sample of geography majors from a lot of different universities, and you find that, wow, it seems that on average UNC geography majors make a ton of money. Then you start to look deeper into the data and you discover that, well, Michael Jordan is in your data. Michael Jordan was in fact a geography major from UNC. But unless your sibling also happened to be arguably the greatest basketball player of all time, it's probably not worth including Michael Jordan in your analysis. Michael Jordan did not make his money from his geography degree. He primarily made his money from his basketball performance, and then the sponsorships, and then the movies. For your sibling, who is unlikely to be that skilled at basketball, we probably just want to exclude that outlier from the data. Another instance where we want to delete the data is when we think that the underlying data is erroneous or flawed. This will actually happen quite frequently, where somebody will mistype information as they are collecting it. You will look at it in terms of an outlier and you will see that it's obviously flawed, and so that there is no way that it can be true. An example that I like to use for this is that in previous year we've asked students of this course to fill out an online form so that we can look at some data. We asked them their height in inches and their shoe size. Somebody reported back that they were 644 inches tall. Obviously, no one is going to be 644 inches tall. Most likely that person was 64 inch or 64.4 inch tall. Rather than try to correct the data by guessing what the correct value was, we should just delete the data. Now, in other cases, we may want to keep the outliers in our data. Specifically, we might want to keep the outlier if, while unlikely, the data point could reflect reality. Again, it may not be a common outcome, but it's a possible outcome. And that's going to help inform the uncertainty around our predictions, because unlikely things might happen. We never simply throw out outliers because they are outliers. We're going to throw out outliers if we know that they are erroneous or if we know that they are not relevant for our topic of study. If it's just an unlikely data point, we probably want to leave it in our analysis, but we want to run our analysis with and without that point. If you do decide to remove outliers, it's also good to do two things. One, you want to check whether your conclusions are robust to their deletion. The big point here is some analysts have had their entire presentation derailed because they got into an argument about whether or not they should keep an outlier or remove it from the data. If you can say that it doesn't affect your conclusion, then there is no point in debating it. So in general, if you delete outliers for any other reason than erroneous data, you're going to want to run your analysis with and without them. Then if somebody asks you, I think that that outlier should have been removed, or I think that this point that you removed should have been left in, you can simply say, hey, I've run the analysis both ways, and it turns out that it doesn't really matter. Then the other thing that you want to do out of honesty as an analyst is you always want to note in any materials observations that were deleted and why you deleted them. You can do this with a footnote or just some comments in the analysis about the fact that you have removed some outliers, how much of your data ended up being removed, and what your motivation was to do that. So let's take a look at potential outliers in the capitals bar data. In our initial data, we can make some arguments about outliers, that maybe some points are outliers or maybe not. Especially that upper point around 2.5 and 175, some student feels that that is an outlier. Again, this is real world data, so we can have some intelligent debate about whether or not a point is an outlier and what we should do about it. But let's say that instead of that Zender's capital grill at 2.5 star and 168 words per review, let's say that instead of being there, it was up here. So in that case, it would have 468 words per review. And what we would do about that? What would we do about the point in that case? Well, it depends on why there are so many words per review and what's the question that we are trying to answer. In that case, any real data seems relevant to the question at hand. We're just trying to understand user behavior with respect to reviews writing. So the question is whether this is truly reflective of user effort or whether it's about something else. We might want to look into the data and say, hey, one of the review isn't actually a review. It's someone who copied the text of a whole book into Yelp. In that case, we would want to just delete that observation and rerun our analysis. It might also be that there is something unique about Zender's capital grill that makes people really want to talk a lot about it. In that case, it would seem relevant to the question at hand, and it does reflect real-world data, so we might want to leave that in. I want to make one additional point with respect to outliers. That is, outliers are not necessarily influential points. Influential points are points that have a significant impact on any resulting analysis or conclusions that we're going to draw. Outliers are points that fall outside the general pattern of the data, but they may or they may not be influential. Influential points, however, are generally outliers. If there is one single point that dramatically influences the overall pattern that we believe exists in the data, it probably by definition is an outlier. But not all outliers are influential points. You can see some examples of that in the bottom graphs. In both cases, the point that is on the x-axis at 1 is an outlier. In both cases, it deviates from the overall pattern that we see in the data, but only in the plot on the right, it actually is impacting the slope of the line of best fit. In the plot on the left, it actually falls exactly on that line, so it's not changing what we think about the relationship at all in that case. So when you identify one outlier, you can also mention if it is an influential point or if it is not. Finally, I want to talk about some important limitations for scatterplots. These are very important and they are likely to have questions related to them in exams. The first big limitation of a scatterplot is that you cannot use it to infer causality. Indeed, a scatterplot alone does not imply causality, no matter how the pattern looks like and how strong the relation looks like. It doesn't matter how highly correlated two variables are or how obvious the pattern is. It simply is not enough to tell that X causes Y or Y causes X. It might be that a third variable, Z for instance, is causing both Y and X. An example would be that you might find a positive correlation between the usage of air conditioning and the sales of ice cream. It's not that AC usage causes you to buy ice cream. It's not either that ice creams cause you to use AC. It's more likely that hot weather increases both AC usage and ice cream sales. Another limitation is that you are generally limited to 2 covariates or maybe 3 at most. I have seen people do some really cool things with the colors, the shape, the size of the points that they put on the plot, and that way they can convey a third variable. But much beyond that, it's difficult to interpret. And finally, subpopulation effects can be masked in the plot. What that means is that when we create a scatter plot, you might have some portion of those points where X and Y may be positively related, and for another portion of those points, X and Y may be negatively related. That especially happens when you mix different subpopulations on the same plot. For instance, you might plot both the populations of bars and the population of restaurants on the review and rating plots that we've seen before. And it might happen that the correlation is positive for bars and it's negative for restaurants. On a scatter plot, that may just look like X and Y have no relationship at all, where in fact there are relationships, but they are different in the different subpopulations.